Hello, this is Lecture 3 of ComSci 123, Arrays and Linked Lists. In this video, we will discuss abstract data types and the basic data structures that are used to implement them, which are arrays, singly linked lists, and doubly linked lists. So first, an abstract data type consists of the following. Number 1, data structure. Number 2, set of supported operations, also known as the interface. And finally, the error conditions. So later on, when we discuss specific abstract data types like stacks and queues, we have to look at each of these three components: the data structure, the interface, and error conditions. As the designer of the abstract data type, we have the choice of which data structure to use. That could be either an array or a linked list. And we will also be in charge of implementing the operations that are part of the ADT's interface. As for the user of the ADT, they don't have to worry about the choice of data structure or implementation details. They only need to worry about whether the ADT is being used correctly and efficiently. For abstract data types, we should know the following. Number 1, operations. So the set of operations are called the interface of the ADT. And what is the time complexity of each operation? So how long does it run? So we already know how to do this because of analysis of algorithms from the previous lecture. And same with memory cost. So we'll do some auxiliary memory analysis as well. Since abstract data types are abstract, the implementation details are not specified. So the internal mechanisms of the implemented ADT should be hidden and inaccessible to the user. So this is information hiding from our object-oriented concepts. So the user should not be able to know the inner workings of our ADT. What they should know is the public interface, which is the set of methods that can be accessed. Examples of standard ADTs include stacks, queues, and vectors, trees, maps, dictionaries, and priority queues. Now, these ADTs in green are called linear ADTs, while the ones in blue are called non-linear ADTs. Okay, so a linear ADT has the following conditions. First, there should be a unique first element in the ADT. There should also be a unique last element. Every element should have a unique predecessor or a previous item, except for the first because it doesn't have a previous item. And finally, every element must also have a unique successor or a next item, except for the last, since it doesn't have a next item. Okay, so all four conditions must be met for the ADT to be called linear. So linear ADTs would look like something like this, right? So there's a unique first, unique last, and each item has a unique predecessor and successor. If one or more of the four conditions is not true, then the ADT is nonlinear. So an example of that would be trees, since trees have not one, but there could be multiple successors after one node, right? That's the difference between linear and nonlinear ADT. Now, let's take a look at the basic data structures that are used to implement these ADTs. Okay, so first we'll look at arrays, and next we'll look at linked lists. So arrays. You're already familiar with arrays from your ComSci 11 and ComSci 21. And an array is just a sequence of indexed items, right? So in here, you have an array of length 8. So the indices range from 0 to 7. And if you want to access the 6th item, you use index number 5. Any array item can be efficiently inspected or updated using its index in constant time. So if you want to get the sixth item, that would be numbers 5. And then if you want to update the third item, that would be numbers 2 equal to the new value. Okay, so just use the index. However, one major limitation of an array is that it should have a fixed array capacity, which must be known in advance or during the creation of the array. So when we create an array, we must specify how many items can the array have, or the capacity. So you've probably done this in your C arrays earlier in your ComSci 21, wherein when you initialized your array, you need to specify the capacity, right? So that's the limitation of array. In most programming languages, an array of length n will have an index range from 0 to n minus 1. So if, for example, you have 10 items, the index would only be from 0 to 9. And you will get an error if you access an out-of-bounds index or an index that is not within the correct index range. Normally, array items are also stored in side-by-side memory locations in most programming languages, or we say that they are contiguous, which is side-by-side. Example applications of array include storing top 10 scores, so you need to have a fixed capacity, so that's only 10, right? You also have multi-dimensional arrays for maps. So for example, the maps in your games are usually 2D arrays, wherein you access, for example, the 0, 0, 0, 1, and so on, nga tile, right? And you also have multi-dimensional arrays for boards, like for example in chess or in snakes and ladders. So you usually have a 2D array for that as well. Okay? Now, for the operations of the array and their running time, let's take a look at each one. Getting an item at a certain index takes constant time, because if you have the index, then you can directly access the item. Updating the item at a certain index also takes constant time for the same reason. And deleting the item at a certain index also takes constant time. So again, if you have the index of the item, it's quite easy to get, update, or delete the item at that index. So constant time lang. If you want to get the size of the array, that's also constant since it's already known at the start, right? It has a fixed capacity. However, if you want to traverse the array or go through each of the items in the array, that will take O of n time, wherein n is the length of the array, or the number of items in the array. So since you have to go through each one, that would take linear time. Same is true for searching for an item. So if you want to find an item in an array and you don't know its index, that would also take linear time, because you would have to traverse the array, and the worst case is either it's in the last it's the last item of the array, or it doesn't exist in the array. So you'll have to go through all items. So that's O of n, or linear. If you get the index of an item, that's similar to just searching for the item, so it's also linear. If you delete an item without knowing its index, you also have to search for the item first before you can delete it. So you have to run search first, so that it takes O of n time as well. Now, if you want to insert an item at a certain index and move the rest of the items after that, that will also take O of n time, or linear. Why is that? At the worst case, we could be inserting the item at the front of the array. And if we do that, then we will have to move all the items forward before we can insert an item at the first index, or index 0, right? So moving all items forward will take O of n, because you are manipulating all items in the array. And finally, if you want to add an item to the end of the array, If it's not yet full, it's just O of 1, right? Because you just simply update the item at the end of the array. However, if it's full, it will take O of n. Why is that? So arrays could be dynamic. We could expand the array if it becomes full. So since arrays have a fixed capacity, what will happen if it's already full and we want to insert a new item? So what you'll do is you have to expand it so that there is room for you to add a new item to the array. So the common technique is just double the initial capacity. So let's say if you have, um, so let's say you initially have an array of size 2. So this will only be 2 cells. So if you double the capacity, it would be size 4, right? Okay. And what you'll do is when you expand the array, you have to copy all items to the bigger array. So item here will be copied here. You also have to copy this one here. Then you add the new item here. Okay. So that is dynamic array. So if you add the item to the last to the back of the array, it's either O of 1 constant if it's not yet full, or O of n if it's already full and you need to expand it. Okay? So that is arrays. Next, we have linked lists. Linked lists are a sequence of nodes arranged one after another, which are connected by links. So it's similar to a chain, okay, wherein you have links from one node to another. However, unlike arrays, you don't have direct access to items. Okay, so let's see what linked list look like. Each node in a linked list contains the following. Number one, a single item or the element. So each node only contains one item, or we also call that the element sometimes. And the node also contains links, which points to either one or both neighbor nodes. So that is the difference later on when we have singly linked lists and doubly linked lists. So a linked list will look like this, right? Each node has an element, and each node also has a link to either one or both of its neighbors. Now, in arrays, items are contiguous in memory, or they are side by side physically in memory. However, in linked lists, neighboring nodes can be physically far away in memory, but they just have a reference to or a link to each other, so we could actually think that they are um, side by side as well. But physically in memory, they could be far away. Now, some of the properties of linked lists are the following. You must have a link to the node to access its item. So unlike in arrays wherein you only need the index to access a certain item, you must have a reference to the certain node to access the node's item. So we'll see what that means in a while. Unlike arrays which have a fixed size, linked lists can have any length. So it's growable. Okay, so you can insert and delete nodes without any problems. So you can grow it as much as you want. And the order of the nodes can also be changed easily because you only need to update the links of the neighbors, no? So which one is the next, which one is the previous, and then you've already reordered the linked list. Whereas in an array, you really have to set the new index and the new item at a certain index for you to be able to rearrange the array. Okay? So as I mentioned briefly earlier, we have two types of linked list. We have the singly linked list and the doubly linked list. For singly linked list or SLL, each node is only linked to one of its neighbors. Whereas in the doubly linked list or DLL, each node is linked to both of its neighbors. So let's take a look at the singly linked list first. Each SLL node contains the item or the data and a link to its successor or the next node. And that's it. So a singly linked list would look like this. You have a node which contains the item and a link to the next node. It's also a good idea to keep track of the head node and the tail node. So in our example, this first node is the head node and the last node is called the tail node. Okay? So for singly linked list, we keep track of the head node and the tail node, and that allows us to easily insert and delete a new SLL node at the front and insert a new node at the back. And we'll see each one shortly. Okay, but that's what we need to keep track. Where is the head node? Where is the tail node? So initially, if it's still empty, the head node would be null and the tail node would also be null, right? Since there are no nodes yet if it's an empty SLL. And then if you have one node in the SLL, that node would both be the head and the tail, okay? Because there's only one. And then if there's already more than one nodes, then you'd have a separate head node and a different tail node as well. Okay, so let's take a look at each um, each operation in detail. So first, we'll insert at the front. But first, let me draw a simple uh, SLL. So we'll have three items. I'll call this A, B, and C. And we will link them together. Now the head node for now is this one, and the tail node is C. So head is A, the tail is C. Now if you want to insert at the front, what we'll do is we'll create a new SLL node with the item that we want to insert. So we'll create a node here. Maybe the one that we'll insert is called X. Okay, so we'll create that node. And then we'll set the new nodes next be equal to the current head node. So this is the new node that we created, and we'll set the next to the current head, which is this one, right? And then what we'll do is we'll also update the head node to the new node. So this will now become the new head node, and this one will no longer be the head. Okay, so that is how you insert at the front. How about at the back? Okay, so if we want to insert at the back, that would be at the tail. So maybe we'll create a new node here. So let's call it D for now. Okay, so we'll create the new node, and then we'll set the current tail nodes next to be equal to the new node. So this is the current tail. We'll set its next to be the new node that we just created. So we'll link them, okay? And then we will update the tail node to equal the new node. So this will be our new tail node now. So this will be the new tail, and this one won't be the tail anymore. Okay, so you have now successfully inserted a new node at the back. Okay, how about if we want to delete at the front? So what we'll do is we want to delete this X node that we just added. So what we'll do is we will update the head node to be the current heads next. So currently our head is X, right? So we will update the head to be the next node, which is this one. So this will become the new head now. Okay, and then what we'll do is we will break. So this is not the head anymore, right? So A is now the current head, and we will also break the link from the old head node to the current head. So we'll also delete this link here. Okay, and now X has been removed from the SLL, and A is now your new head node. Okay, so we can also delete this one now if you want to. Okay, so it's pretty straightforward. But how about if we want to delete at the back? So if we want to do that, we have to, if we delete D here, we have to set the tail to be equal to the previous one, which is C, right? However, the problem is there is no reference to the tail's previous node. So you cannot link back to C because there is no previous link. There's only a next link, but no previous link, right? So what we'll need to do is we will have to traverse from the head all the way up to the tail in able to access this one so that we could change this one to be the new tail. So what we'll do is we'll start from head and then we'll keep going to the next, and check if the next one is already the tail. If it's already the tail, we'll stop here and we'll make this the new tail, right? And we'll also delete the link from this one to this one, okay? And then now D has already been removed and we have set C as our new tail, okay? But you see that it is costly to do deletion at the back because we have to traverse from the head all the way down to the tail, okay? So that's it. Now, for SLL traversal, I briefly mentioned this earlier. We start from the head node and then we go to the current node's next node. So we follow each node's next one until we reach the tail node. So if we want to traverse the whole list or we want to access each item, then we start at the head, follow the next, follow the next, follow the next until we reach the tail node. Okay, so that's SLL traversal. Now, if you want to insert after a node, this is what we will do. Okay, so assuming that you have reference to something called the current node, this is how you'll insert after that current node. Okay, so let me draw this one first. So let's say that you have, say, A here, and this is maybe C. And this is the node that we have. And currently, A is linked to C. Okay, so given that we have a reference to node and we want to insert after this one, these are the steps that we'll do. First, create the new SLL node with the item. So maybe we'll create it here. Maybe the item is B, right? But it doesn't have any links yet. And then the new node's next should be set to the node's current next. So this was the new node that we created. Its next should be set to node's current next, which is C. So we will link this to C here. And then set node's next to be the new node. So we will set this next to new. So what will happen is this link will be gone now, since we've updated the nodes next to be new. So now you have inserted after the node, right? This one. So you have inserted B in between A and C. Okay? Next, how do we delete after a node? So maybe we want to delete B, which we just added now. Okay, so as long as you have a reference to the current node, which is A in this case, here's what we'll do. The del node, or the delete node is what we'll call it, will be the current nodes next. So the delete node is actually this one. Or let me rewrite that one here. So this is the node that we'll delete. Okay, and then we'll set nodes next to be equal to delete nodes next. So we'll update the next of node to the next of del, which is currently C. So we will update this next node to C. So what will happen is this will be broken now. Okay, and we also have to break the link from del node to the next. So we'll also have to take care of this one. So wala na siya link. And now we have removed B from the SLL. Okay, so A is now linked to C and B is left alone. So that will be deleted. Okay, so it will now be gone. So that is how you delete after a node. Okay, so for other SLL operations, so we have seen that if you insert at the front or at the back or after a node, that only takes O of one time or constant time because it only needs 3 steps, right? So you create the node, you update the next, and then you update the either the front or the back, the tail na pointer, right? So constant time for this one. However, if we insert before a node, it will take O of n. Why is that? Because we will need to we don't have access to the node before the current node. So what we'll do is we have to traverse from the head node all the way to the current node, and that could take O of n time. Okay. If you delete at the front or after a node, that's also constant time because you can do it in 3 steps. But if you delete at the back, as we saw earlier, or before a node, it will also take O of n time because again, we don't have a reference to the previous node. So we'll have to traverse from the head node. Okay. If you want to update an item at a certain node, that takes O of 1 as long as you have access to the node that you want to update. But if you are looking for a certain item, so you search for an item, that would take O of n because that entails traversal. Okay, so you will need to examine each SLL node to look for the certain item, and the worst case is either the item is at the last part of the node or it doesn't exist, right? The same is true for deleting and updating an item without any node reference. So if you don't know which node the item that you want to delete or update is in, you will have to look for it again. So it's similar to searching. It's also O of n or linear time. So as I've mentioned, traversal takes O of n time. But if you want to do reverse traversal, that means that you start from the back all the way to the front. That would take n squared or quadratic time because for each node, you would want a reference to the previous node for you to be able to go backwards. But as we've mentioned earlier, we don't have a direct access to the previous node, so you'll have to traverse from the head to the current node. So it takes O of n squared. Okay? So that is singly linked lists or SLL. Next, we have doubly linked lists. Each DLL node contains the item or the data, a link to its predecessor or the previous node, and a link to its successor or the next node. So this time, it has access to both neighbors, okay, the next and the previous node. So it will look something like this. So the DLL node has the item and then linked to the previous node and the next node. Okay. And in DLLs, we have something called the sentinels, which are special nodes. So we call them the head guard and the tail guard. So these sentinels are dummy nodes that don't store any items. So they don't have any items in them. They are just there to guard the head and the tail. So it would look something like this, right? So if your DLL has 3 items, you have 2 extra nodes, which is the head guard and the tail guard, which actually doesn't store anything. Okay, so that's it. So if you have an empty DLL, it will only have the sentinels. So an empty DLL will only have the head guard and the tail guard. So it would look something like this. So if the DLL is empty, it would look something like this. Okay, this is one DLL node. This is another DLL node. So we call this the head guard and the tail guard. The head guard's next would be the tail guard, and the tail guard's previous would be the head guard. So that's it. This is what an empty DLL will look like. But again, it doesn't have any items. So null na siya. Okay? And then, this two never changes. So in SLL, we update the pointer to head nodes and tail nodes. And even the head and tail nodes could even be null at the start or even refer to the same node if it's only one. But the head guard and the tail guard will never change. So um, they will be there until the DLL is destroyed. And only nodes between them change. Okay? So inserts and deletes can now happen between a pair of existing nodes, since our head guard and tail guard will always be there. Now, to compare SLL and DLL operations, for SLL, we only update the next, but for DLL, we update both the next and the previous. Okay? And in DLLs, it would now be easy to delete at the back because you now have a reference to the previous node. Because recall earlier in SLL, the problem was we did not have a reference to the previous node, and we wanted the previous node to be the new tail. But now, since we have both links to the next and the previous, it's fairly easy to do so. Okay, so let's see some examples of DLL. So to insert at the front, so this is your current head guard. So you'll create a new node here, and then you'll set its previous to the current head guard, and the next to the current head guard's current next. So the old first item, basically. So in next niya, de. But we also have to update these links, right? So we have to update the head guards next to be the new node, and this first item's previous to the new node as well. So this link and this link are updated here. So we have now inserted at the front. Okay. If you insert after node, it's fairly similar, but instead of the head guard, it will just be a certain node, right? So add a new node, set its previous to the node that we are inserting after, and then ang next niya is the node's current next. And then we'll also update the next of the node to be the new node, and the previous of the um, node's previous next, or this one SFO, uh, its preview should be set to the newly added node. Okay, and then if we delete naman, so this will be the same whether you delete at the front or at the back, it's the same, because anyway, you can treat the head guard and the tail guard as just another node, right? So if you delete after a node, you have this one, we'll delete this one after JFK. So we will have to remove the links from here to here. So we'll delete that one, and then we'll update the links to jump from this node JFK all the way to SFO, because now we don't have PVD in between, and SFO to jump at ang previous niya to be set to JFK, since we don't have PVD in between, and then finally you can delete it. Okay, so it's just a matter of updating the previous and next links. Okay, so for DLL operations, inserting at the front, the back, before or after a node takes constant time, since you have access to both previous and next nodes. Same with deleting at the front, back, before or after a node. That's also constant time. If you also want to update an item at a certain node, so as long as you have access to the node, you can update the item pretty easily, constant time as well. But if you search for an item, it's still O of n, because you will have to traverse through the whole DLL at the worst case. So either it's at the last of the DLL or at the um, or it doesn't exist. Now you might say, sir, if it's at the last, why don't we just start at the tail guard? We could do that, but we don't know whether the item is at the front or at the back. So we have to start somewhere, but there is no assurance that where we start is where we'll find the item immediately. No, so at the worst case, we still have to traverse or go through each item. Okay, so it's still O of n. Same is true when you delete or update an item without any node reference. So you just know that the item is somewhere in the DLL, but you don't know which node it is. So that will also entail searching or traversing the DLL. So that will also take O of n, or linear time. So as I've said, traversal takes O of n, but this time, ang reverse traversal for DLLs will also take O of n. So remember earlier, for SLL reverse traversal, it took O of n squared, because if we want to go backwards, there is no direct link to the previous node. So we have to traverse again from head to the current node to get the previous. But in DLL, since we have direct access to the previous node, then it's pretty straightforward to just go backwards. So starting from the tail guard, then go previous, 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 until you get to the head guard, right? So it's also linear time to do reverse traversal. Okay, so that's DLL. So in general, how would you know when to use an array or linked list? For an array, you usually use them when you have frequent random access operations. So for example, you want to access item number 5 or item number 4 or item number 99 or 74, something like that. So that's random access. So we can do that easily with arrays because they have the index. We can't do that quite easily with linked lists, because if, for example, if you want the 99th item, you will have to traverse from the start all the way to the 99th item, right? So if it's frequent random access operations, use array. But if your data structure has frequent capacity changes, then use your linked list, because the linked list could expand on its own, right? There is no need to copy items, unlike the array wherein it has a fixed size. So if it becomes full, you have to expand it manually. Okay, so that would be your guideline in choosing whether to use arrays or linked lists. Okay, so that's it. Let's review what we discussed so far. So we talked about arrays, which is one of the data structures that we could use to implement our ADTs. And arrays are nothing but a sequence of indexed items. So index is the key part of the array. And then we also have linked lists, which are composed of nodes that are linked to each other. So we have the singly linked list, which only references the next node, and the doubly linked list naman, Each node references the next and the previous node. Okay, so we will use the arrays and linked list later on to implement our abstract data types like stacks or queues. So we'll learn more about that in our laboratory class. Okay, so that's it for today. And in our next topic, we will take a look at the first two ADTs, which are stacks and queues. And then there's an extension of a queue, the double-ended queue, which is called a deck. Okay, so that's it for today, and I will see you next time.